Hi, I will present the paper on the range and capacity of LoRa 2.4 GHz. I am Andrzej Duda, and this is a joint work with the Reyhane Falanji and Heusse. Here is the overview of my talk. I will start with the background on LoRa, discuss some related work, present our simulator of LoRa 2.4, and give some simulation results. LoRa is a long-range wire network based on a chirp spread spectrum. It operates in a 868 MHz ISM band in Europe. It has a limitation of using only 1% duty cycle, and it uses a simple unslotted Aloha access method. Its range is around several kilometers. And capacity is fairly good with over 1,000 nodes that can achieve 60% PDR in the range of 5 kilometers. Standard LoRa depends on several parameters. So the bandwidth may be up to 500 kilohertz. The bitrate is fairly low, up to 5 kilobits per second. The most important parameter is the spreading factor that defines the number of bits per chirp. For SF7, for example, the duration of the transmission is the shortest one, and with increasing the number of the spreading factor, we double the duration of transmission. However, we gain in robustness. For SF12, the frame duration is fairly long, around 2.5 seconds. There is also some FEC added to the transmissions, giving us some coding rate. The link budget is fairly good, allowing for some long-distance transmissions, for example, with the satellites. LoRa 2.4 GHz provides higher bandwidth up to this value, and also higher data rates. And also, compared to standard LoRa, we have the spreading factors from 5 to 12. There are only few papers reporting on the performance of LoRa 2.4. In the first paper, the results was the following. Point-to-point measurements over a lake, and the range was around 2.2 kilometers with a SF12. Other papers reported measurements in urban environments, and you see that the range was around 500 meters. The papers emphasize on the dependence on channel conditions. However, the previous work didn't take into account contention and collisions. We have developed a simulator in Python for LoRa 2.4 GHz. It's an extension of an existing simulator for standard LoRa. The principle of simulation is the following. So we have a gateway in the center of a cell, and we assume some density of nodes that are uniformly distributed in the space around the gateway. Depending on the distance of a node, node will use a given spreading factor. So for example, here, this node will use SF9 because of the distance from the gateway. All nodes in a given annulus using the same SF will compete for the channel, so there may be some collisions. The greater the space where the nodes using the same SF are, there are more nodes, so there may be more collisions. We can observe this effect for example, SF12. We assume different channel propagation models. So this model is specialized for the band around 2.4 gigahertz. So it's specific for LoRa 2.4. And we also assume Reyhane models and Rayleigh model for small-scale fading. We take into account collisions of the nodes using the same SF, and also the capture phenomenon in which stronger transmission may survive collisions. We assume the following parameters in simulations. So we assume that applications require some target PGR. We take two values, 60% and 90%. So some applications may be happy with the 90%. For some applications, using 60% may be good if they use some repetitions or repetitive codes to obtain reliability. We assume that the SF boundaries, changing the SF value, depends on SNR or the target PGR, so these values. We assume low and high traffic density and node density, which results in low or high load. And also we consider different channel propagation models. So Reyhane that corresponds more to an open space, and Rayleigh fading corresponding to urban environments. The parameters are the following. So we have intensity, traffic intensity. Here is a low, high value with the high density of nodes. This gives us high load. Low intensity with low density of nodes results in low load. We use this payload size, two different bandwidths, the channel path loss model and fading models in our simulations. The simulations are in three parts. First, we compare with the measurements reported in previous work. Then we consider the comparison with standard LoRa. So we assume the similar parameters as in the previous work on capacity of standard LoRa, the same interpacket interval, and we see how the range and capacity changes. And finally, we consider the performance of LoRa 2.4 for various parameters, so the low target PGR and types of fading. Here is a comparison with measurements. So the experimental work observed this range for SF12 over an open space in an open space environment. Our simulation gives kind of a similar value, and we also report on different shorter range for different channel models. Comparing with the standard LoRa, we use the same interpacket interval. However, we assume a higher bandwidth, and we use Rayleigh fading, which was also used in the comparison with standard LoRa. The boundaries are determined based on SNR, so they are fairly short. They are fairly short compared to standard LoRa. Here are the results. So low density, high density, and we can observe that for low density, all nodes within the range of 800 meters obtain at least 60% of PDR. For higher density, there are some nodes they cannot obtain 60%. So this is due to collisions for large SF. And the range, this was about 550 meters. In the standard LoRa, the range is much longer, 5 kilometers. Here we have something which is under 1 kilometer. Now, some results for various parameters of LoRa 2.4. First, we can observe that for low load and open space conditions, the range is around 1 kilometer. And this is for the target rate of 60% and target rate PDR of 90%. For high load, the range is even shorter, so 700 and 500. However, we can observe that for these high load conditions, the capacity still is high compared to the standard LoRa, for example, of 1,500 nodes. If we change conditions to Rayleigh, so we have Rayleigh, low load, and PDR of 60 and or 90%, we can observe further decrease in the range. Okay, so we go to 800 or 400 meters. This is for low load, so the capacity is still low. But if we consider high load, we obtain the range, which is around 500 meters or 200 meters, but the capacity is still good, almost 900 nodes in the range of 500 meters. And this is for Rayleigh, so it means that corresponds to urban environment. To conclude, we can observe that our simulations give the same order of magnitude as the method range in the previous work. The comparison of with standard LoRa gives us much shorter range, so 5 kilometers compared to some under 1 kilometer range, with the capacity which is still good compared to 1,500 nodes for high load. For high load and in open environment, the capacity is still good compared to what we can expect in standard LoRa. For PDR of 60%, we have the range of 700 meters. For the urban environment, so the Rayleigh fading, the range is much shorter, with the capacity which is much lower because of the PDR of 90%. Thank you for your attention.